Mirzakhani, and she will speak on
dynamics on the moduli spaces of flat structures. Maybe I'll write it down. Thank you, and thanks. I would like to thank the organizers for organizing such a great workshop. I think it would take me some time to digest all the things that I heard about, but it's great to be here at MSRI. And I would like to talk today about some problems and some recent progress related to dynamics on moduli flat structures. And it's a little bit tricky to give this talk in front of this audience, and I'll try to maximize the number of people who are not terribly bored or terribly confused. So I'll try. And so it's a big. Okay. So what I would like to discuss today is the action of SL2R and dynamics of the action of SL2R on moduli spaces of flat structures on a surface of, so this is on a surface of genus G. And the space here, so I'm going to be, I don't want to start from billiards. That's one thing. And I'll just tell you some things about the action on this, the nice things and the tricky things, and what we can do, and some open problems. So I think there were some discussions about flat structures coming from unfoldings of billiards, and these are natural things to consider, to study. And the space, maybe I'll just say something about the space. Every point in the space is actually a holomorphic one form, omega, on a complex curve of genus or hyperbolic surface, or a complex curve of genus G. And just in case you have not ever seen this, which is very unlikely, but this is the moduli spaces of hyperbolics. So this, pairs X omega, which is that you have, you're fixing the singularity types of the set of zeros of this form. So you're basically saying, oh, this is locally like dz, but some places, of course, you don't have this if your genus is bigger than or equal, strictly bigger than 1. So some places you're forced to have zeros, and you're keeping track of those zeros. And even though I don't want to do the flat surface type things here, it somehow it's important. And as we will, I'm trying to get to the point where I use some of these things. So I would like to say that this X omega defines, so I don't want to start from billiards, but this X omega defines a flat structure, basically using the form dz apart from the k singularities, defines a flat structure with somehow mild singularities. So maybe you have a surface of genus 2, you have 2 singularities, but apart from the singularities, the first surface looks flat. And so the interesting thing about this subject is going basically back and forth between the action of SL2R on this moduli space that I'll tell you. Maybe I should define it, even though I don't want to. But and the properties of elements here, geometric properties of the elements here as flat structures. And these flat structures basically is like curvature 0 apart from, you're pushing all the negative curvature that you have to have because the genus is big, and Gauss-Bonnet type theorems, to finitely many singularities. And so basically now what happens about the flat structure is that like the structure of geodesics, like you can talk about closed geodesics even what about the regular geodesics? So regular geodesics, and there are some nice results about flat structures or this type of flat so-called translation surfaces, which says that basically every homotopy class that I give you can be represented by a geodesic. Geodesic means that you have a flat structure, so you have R2, distance function with respect to R2. You can try to minimize length. The problem, and there is always so you have uniqueness of geodesics, mostly apart from what we call so regular geodesics that don't go through the singularities at all, and these are called cylinders. Because you see a flat cylinder when you have a regular geodesic, you move, with respect to this flat structure, you move it a little bit, and it really, with respect to the flat structure, is a flat Euclidean annulus, and you go through the singularities maybe on the boundary, and they're forced to be parallel to each other, what you see on the boundary. Apart from these, if you give me a homotopy class of a curve, it's a very delicate, tricky thing to see what the geodesic does. It's not as nice as the hyperbolic or strictly negatively curved manifold. So these are cylinders, and they are very important, and it's if you try to understand the geometry of X omega. And before I start saying some basic things about this, I should say that even the existence of one single cylinder on an arbitrary flat or translation surface is not trivial, and this is due to, I'll refer to these things, and just in case if you have not seen this, due to work of Mazur, who used actually the action of SL2R on the moduli space. And also, I think Vorobets has some arguments for getting these, and you don't see the SL2R action, but you see that it acts. He just doesn't talk about the moduli space, but the action is there. So even finding one cylinder uses the action of SL2R on H. Okay, but what I would like to see is that, so can you find, is there a cylinder which takes up between, every cylinder has some volume. The flat structure, Euclidean structure that you get on the surface will give you volume. Is there a cylinder C which has volume, say, between C1 and C2? Can you find two cylinders which are, can you find three cylinders? Yeah, what can you say about the geometry of these things and the geodesics on this? And there's a lot of, and these are, very nice questions, and some of them have been studied in terms of the SL2R action by Eskin Mazur, Zurich. I'm just going to say a lot of names because I feel bad if I don't do it, but it all uses dynamics of SL2R on the moduli space. Okay, but okay. So what are the things? Maybe I should tell you how the action is, even though I don't want to, but I think I have to say something. So how would we just look at the HA1 to AK? One way of basically studying it, or the action of SL2R, is just by looking at, start from a triangulation by geodesics that only go through the singularities at their endpoints. Okay, I'm not even going to draw this one. And then if you have a one form and you have delta and you have a one form omega, you can basically integrate omega around delta and look at the holonomy of basically omega around delta and get a number in C. And there is a result that says that if I give you Q in HA, which is A1 to AK, in an open set around, basically an open set U around Q, the map, which is the holonomy of Q, around the triangulation which has edges delta 1 to delta m, and I'm not telling you m, you can write in terms of g and k. This determines your Q. So it's sort of it. So what I like about this is locally very nice. And SL2R acts by, if you have a set of numbers in C, you act, if you have A here, A acts here too. So that's the action. Locally, it's very easy to see what it does. But what makes this very tricky is that what makes it nice is that this SL2R action keeps the structure of all the geodesics the same. And that's why all these results can use the SL2R action. But any other way you want to deform your surface, you're gonna basically lose some geodesics. So it's very hard to see what other deformations. Even if you move this slightly a little bit, there are some very long cylinders that will break down, and there's no other way to stay away from the mess except for the SL2R. So that makes the SL2R action very natural if you want to look at the structure of geodesics of flat structures. So, okay, before I get into the problems that I want to discuss, maybe sorry? Bigger. Okay. Okay. So I just don't make it smaller. Let's try to say. So, overview for the SL2R. This is in case, you haven't seen these before, but I apologize for the ones who are terribly bored. But okay, so the action of SL2R on H. So what are the basic things that we would like to know, and why homogeneous dynamics is relevant is that there are lots of nice properties of this action SL2 on HA, which is 2G plus K minus 1 complex linear space. And it has some, it has some singularities, but it doesn't matter. We can go to a finite cover, and it looks really like this linear thing, patching of linear things together. And this, the action of SL2, it has 2 parts. So you can also look at the action of like the geodesic part of the action, and this behaves really like a nice geodesic flow. Almost. There are lots of closed geodesics. There are even closing lemmas. Closed geodesics are defined over number fields of degree at most 2G, or some bound depending on G like this. And not only that, so these are things that I don't want to discuss. One issue that we have here is that this space, of course, is not compact, which is nice, and also, it causes problems, but it's also nice, as hopefully I'll get to discuss. And it's non-compact, of course. You can imagine you have these singularities, and they get close to each other. For example, that's one way you can get out of HAI. You can have closed curves which shrink. You can have, but even the non-compact part is pretty hard to, so in a messy way, it's pretty hard to handle. And no matter what you do, they're there, because it's not only about, it's not like hyperbolic surface degenerating. You can lose parts of the surface completely. They can have a small subsurface, then a big subsurface next to each other, and it's just, and they can be all over the place. So it's hard to handle these things. But okay, but however, the action of GT. So here I'm going to just list some names of people who have worked on these things, and I just want to sort of motivate it for people who do homogeneous dynamics. This is the geodesic flow is non-uniformly hyperbolic. So you have the nice things. So this is, I don't know, this is nice and naughty, but I'm not sure it's all mixed. The non-uniformly hyperbolic. This is due to work of Forney and Veach. So maybe before even I discuss these, there is results by Veach and Mazur that say that basically the Lebesgue, there is an invariant measure in the Lebesgue measure class if you fix the area of these flat surfaces, and you get the action is ergodic. It's very much like the action of SL2R in the basic properties on SL2R divided by SL2Z, meaning that the geodesic flow is ergodic. The geodesic flow is mixing the Horst and the Horst cycle flow is ergodic. The Horst cycle flow is mixing. You have non-uniform hyperbolicity. The other nice thing is that the stable, unstable manifolds are quite nice, and they have geometric meaning. But these are off. I'm just mentioning these things, but there are lots of interesting things due to many people. Veach, Mazur, Forney, and a lot of people in the audience have done work on this. But I just want to say what is known. And the other thing is about the Horst cycle flow. So UT is also ergodic. And maybe I'll mention this. Maybe the one very nice result that we know, a few things that we know about the Horst cycle flow that I would like to use in this talk is the non-divergence of the Horst cycle flow, meaning that exactly like the case of the homogeneous setting, if you have this unipotent element and geodesics can do crazy things, but Horst cycles are well behaved. They can't diverge to infinity, even though this infinity is very complicated, which is the Dani-Margulis type statement. And in this setting, it's due to Minsky and Weiss. And also, minimal sets are nice, and I'm just sort of following at what we heard in other talks, and that's due to Smiley and Weiss. For the Horst cycle flow. Okay. So, I don't know how much this all makes sense. So so I want to discuss some problems. So you want to see if the action of SL2R, look at the invariant closed sets and orbit closures of SL2R on the space. Okay, so and I would like to mention the theorem that I don't want to discuss too much, but so basically you'd like to look at the action and see, like if I give you a point, you want to see if the SL2R action becomes equidistributed or not, where it goes, what the closed sets are, because we have the UT part, which is unipotent, so based on the results of Ratner, Margulis, and a lot of like amazing work in the homogeneous dynamics. You want to see if you have the same thing in this setup, which is not homogeneous. And, okay, but however, even though this is not homogeneous, thanks to Alex Eskin, and we know that we can use a lot of and this is also joined with Mohammadi, that in fact, so it's, so I'm going to be very, we can use a lot of techniques in homogeneous dynamics. Unfortunately, I don't have time to list the name of type of things which go into proof of this theorem. Closures are, again, the right affine. And affine meaning that they are, so I would like to look at it in terms of the local picture, which you have the holonomies of some saddle, these are called saddle connections, of holonomies of some arcs, which are geodesics at the point. And again, if you have some SL2R orbit closure, and the same thing would be for invariant measures, they're supported on some affine piecewise linear subspace. So basically, this means that you can locally write it down as the set of zeros of some linear equations with coefficients in R. And yes, so maybe I wanted, okay, to remark, this I'm not going to talk about much except for the statement. And you can do it for measures, and then you can get the result for orbit closures. But that's all. I want to give a few remarks about this theorem. One is that, so the genus 2 case was done by Kalta and McMullen. And this is not only the special case of this result. It's so what McMullen does actually, as I hopefully get to mention, it's more geometric and less homogeneous dynamics. So the proof uses Ratner's result for SL2 cross SL2. But apart from that, you really see what your surfaces are about, and the geometry is there. This theorem with SK and Mohammadi, there's less of that. So this is mostly homogeneous dynamics, except for results of Forney, there's some parts which are not homogeneous dynamics, but a lot of it is homogeneous dynamics. And I've learned a lot just collaborating with Alex about homogeneous dynamics. But it doesn't see the surface as much. Okay, but however, the thing that McMullen did is more about the surfaces, and it's stronger in the sense that it's a classification. And so even in this simplest case, so maybe it's not the simplest case, but maybe the most basic case is when SL2R orbit of a point is closed. And if you went to this beautiful talk by Alex Wright here, you see that that's a very tricky problem. Even if you want to see what are the orbits which are closed under the action of SL2R. So basically, it's like a three-dimensional thing in your space because you have SL2R. I'm fixing, sometimes I'm fixing the area 1, so I get really a three-dimensional thing. And you want to see when it's closed, and if you can classify those. And in general, it's very hard. So these are called Veitch surfaces. So basically, these are like hyperbolic surfaces sitting inside your HA1 to AK. And there are, as the name suggests, there are examples by Veitch. There are, and I'll mention some, I'll comment on some constructions of these, but getting all of them is very hard. And of course, you can cheat. You can start from some torus, put some Mark's point, and take ramified covers. But if apart, and that will give you infinitely many things. And whenever you have an example, you can take ramified cover, get infinitely many things. But there are very few sets of, constructions for Veitch surfaces, which don't go through this taking ramified cover. And what in the genus 2, what happened, what Kurt did was that he classified not only, all these SL2 things and the Veitch surfaces as well. And I'd say in a more geometric way. So, okay. So maybe I want to mention some problems before talk more about these SL2R invariant closed manifolds, which are important if you want to understand, basically, given Q, you want to understand the SL2R orbit. Basically, just knowing that it's an affine thing doesn't give you, even if it's very nice, it's hard to say what the SL2R orbit is, because you get if you have these affine invariant manifolds, then you have SL2R action there, and they have rich geometry and lots of interesting things happening there. So maybe before I, so the problem, of course, is one is the the classification of these affine SL2R invariant manifolds. But maybe before that, I want to say the one thing, because I want to say something about them, give you some invariants. Before that, is a more difficult problem is saying things about, I go between H and U, UT invariant, maybe this is a very big problem, measures and orbit closures. Can we say anything nice about them? And as I mentioned, basically about UT, unfortunately, we don't know anything about the divergence, or we can't apply things like Ratner's proof does. So, and the results here are mostly really using the GT in a very strong way, and entropy and all the things that you get if you have this geodesic flows. The UT part is very mysterious, except for the non-divergence that I've been using quite a bit in many my collaborations, but it's very hard. And there are actually Smiley and Weiss, they have examples of somewhat badly behaved Horst cycle flow invariant sets. But still, I think, even though maybe I'm a little too optimistic, they're thinking at least the orbit closures, behind every crazy orbit closure of UT, there should be a nice SL2R invariant thing. And at least the counterexamples we have so far, they are not so bad. They're not like Cantor set type things, or they are still coming from some nice SL2R invariant set. So there's some hope. But so there's another thing that, again, these are very ambitious maybe problems, but there are things that you can, I mean, even partial results would be very useful for these kind of problems. The other thing is, going to be very ambitious, is like, if you know about SL2R orbit closures, can you make any things with rates of, so as we heard in Elon's talk, but this is like the SL2R, you can take balls of radius r in one copy of SL2R. The result that we have is that actually stationary measures are the same as invariant measures. So if you take balls and make them bigger and bigger, they become, say, even if you know that they become equidistributed, you want to say how fast they become equidistributed. Okay. Again, in general, probably very hard, but still, I think there are lots of interesting problems. And the third one, before I get into a more refined version of the classification problems, that, okay, this classification problem, I think, is not, it's not so easy. It's saying something about the general things, but there could be quite interesting things about so-called finiteness results. And here, since I'm not good with giving the names of the people who have worked on this kind of thing, maybe I want to mention a few things. So, in fact, the finiteness results, for example, means that if you want to say, okay, maybe there are some Veitch surfaces in genus 3, an abelian differential on genus 3, it's probably very hard to classify them. But you can prove that there are like maybe finitely many of them. Or you can, there are just some, but is that the case or not? So there are results by, okay. So maybe so Bainbridge, Muller, I think Habiger, this is the genus 3. And so maybe I should say that it seems that for understanding SL2R orbit closures, algebraic geometry is very essential. I'm not necessarily very happy about it, but maybe it's the fact of life. So, and actually Martin Muller is one of the people behind bringing some ideas from algebraic geometry to the field, and especially if you have a Veitch surface and it's algebraically primitive. I'll comment on this. So basically it means that if you write down the equation of this piecewise linear thing, there's no equation in Q. So for example, if you have a ramified cover, there are lots of equations in Q because you have parallel things with rational ratios. So, but algebraically primitive means that being far away from being a cover, maybe. At least there's no Q. There's no equation in Q. When you write it in this setting, then they prove that in genus 3, in different, okay. And in general, I guess Muller proved that so it doesn't matter what this, in some cases, they are finitely made. Their finiteness results in this direction. Then, and they're pretty hard. I mean, this uses, my understanding is that it uses really non-trivial things, and it's long and it's computer assisted. Not easy. The other direction, so Alex, if you have, I'll write rank 1, but I'll discuss rank right after this. There are some finite results by Anu again and Alex Wright. Then there are finite results in prime genus. So finiteness results means finiteness of Veitch surfaces, algebraically primitive prime genus by Matthews and Wright. And and my understanding is that there will be many more of these type of results, probably even in the next few months. So this, but it's I just want to give you one of the problems, and there are many partial results proving finiteness results. So this kind of thing you can do with algebraic geometry. You can just try to find all the Veitch surfaces, or you can use basically this kind of the other type of thing would be that you have a sequence of Veitch surfaces. If they are infinite, they become equidistributed in a bigger affine invariant submanifold, and try to say that doesn't happen. Again, a non-trivial amount of algebraic geometry seems to be necessary, and maybe I'll mention Simeon Philip, even though he's not collaborating with any of these, but it's algebra geometric ideas. He did a lot of interesting things in this direction. And let me see if so in general, it seems that except for, there are a few families of, infinite families of algebraically primitive Veitch surfaces, but it seems that we might know them all up to this finiteness type thing. But yeah, I don't think this is a complete list. But okay, but I think it's very interesting to know finite results for Veitch surfaces or other SL2R invariant things. But just the existence of Veitch surfaces is already very, very, very surprising, as I think Alex Wright mentioned in his talk. And okay, so how much time do I have? Let me check the.
15 minutes.
Oh, okay. That's good. So, okay. So what I want to talk about today is something a little bit more about these SL2R orbit closures. And it's more about an approach that might show that there are not so many of these SL2R invariant manifolds, hopefully, maybe, or give you an intuition of what they should be like. So like roughly, you want to say, okay, Weech surfaces are complicated, but behind every SL2R invariant affine manifold, there are some Weech surfaces, non-trivial Weech surfaces. So the construction of the more complicated ones would give you Weech surfaces. And if hopefully one day when an algebraic geometry will come and say, oh, look, we know all the Weech surfaces and they satisfy these properties, you can basically boost, get results about general SL2 affine invariant manifolds. And my understanding is that it's a little bit like it might be more like what I would like to do is more like what Danny and Margulis were trying to do by doing somehow getting inductively as the invariant manifolds. So okay, so I would like to say some joint work with Alex Wright in this, but before I start, I have to, maybe a few minutes, I have to say a bit about this SL2R invariant affine manifolds. So there are two nice invariants that you can associate to one of these affine manifolds. One is rank, and this is, and both of them, so I'm going to just give you an overview, but so they make sense and they are nice because of work of Alex, right? So if I give you a SL2R invariant, you can define a rank, which is, so I'll call this M, rank of M, which is something between, could be an integer between 1 and the genus. So for example, if you have a Weech surface, the rank is 1. The way Alex defines it, if I understand correctly, is you see the dimension of the space in A1 to AK when you restrict it only to the parts coming from absolute homology of your surface. Not, so for example, if you just put some conditions on the relative homology, rank is G. But if you put more conditions, the more conditions you put only on absolute homology, the rank goes down. But the way I would like to think about it is the maximum number of non-parallel cylinders which are disjoint on Q in M. So if you have a point Q in M, you can, okay, if rank is 1, if you have a Weech surface, one nice property is that if I give you a cylinder, the whole surface will decompose into cylinders in that direction. So there's nothing, if you have one cylinder, there's no non-parallel cylinder which is disjoint from it if you are on a Weech surface. But sometimes you have 2, sometimes you have 3, and of course I'm hiding some technical things, but basically that's the notion of rank. You just look at the absolute homology part. And that's actually seeing that this rank and that rank are the same. You can do it using non-divergence of the whole cycle flow. But maybe, hopefully I'll get to comment on that. The other thing is, again, by work of Alex, is field of definition, which is a number field of degree less than or equal to G. And what it means is that, so I tried to, hopefully it's still on the board. So we have this closed geodesics on the space. Sometimes when you go along GT, you come back. And in that case, actually all the holonomies are basically defined. You can make them by rotation all to be in a field, which is degree G. But in fact, So field of definition, you can look at it and look at all the closed geodesics in your invariant manifold and see what fields you get from them. And if you get crazy fields, then the field of definition is sometimes Q. So this would be an example. If you have ramified covers of lower dimensional stuff, lower dimensional stratum. So there's no, basically field of definition means that when you write down the affine manifold as a set of like zeros of some equations, you can make those equations all to be in this field. And the field of definition, for example, Veitch surfaces, they have field of definition. Just coming from one closed geodesic, you know how everything is working out. So there's rank and there's field of definition, and part of the problems, so you can basically separate out the problems that we had about measure classification on, are there somehow, for example, one big question is, can you find M defined only by Q, which is not a ramified cover? Also, so we say M is algebraically primitive if degree of the field of definition is G, is the maximum possible. So that means there are no Q relations. Everything is all the relations are in terms of this number field F, and the number field F is the maximum possible, has maximum possible degree. And just one more comment about Alex's work, which I find very interesting in this. And at first time I saw it, I thought, okay, this is going to finish up measure classification, but of course I was wrong. But still, I think it's very useful. So this is, again, the theorem of, right, is that if you have Q in M, and here I put generic, but this is not important, just I don't want to get into some technical difficulties. So Q in M, and if you have C1 to Ci, parallel cylinders. So I'll just give you an example since I don't have time. If you have some parallel cylinders, maybe I should put it in quotation because I'm not going to write down the most general form. If you have a bunch of cylinders, I will write cylinder deformation is in M, or M is invariant under the cylinder deformation. But what I mean by that, if I look at my cylinders, you can open up the cylinders. Okay, there are different geometric ways you can deform a flat structure. SO2R action is the nicest one. But if you have a cylinder, there is a very nice deformation that you can sort of explicitly understand. You can just make the cylinder longer, open up the cylinder in some direction. Say, give you a direction, make this longer. And if you have parallel guys, make this guy longer too, proportional to the width. And what he proves is that if you have these parallel cylinders, you're in the strong part is really the nice thing is that if this affine invariant manifold, if you have Q, is invariant under this opening up cylinders. So you got one on more direction, or many more directions. So it makes it even less likely that you have these affine invariant things. It's amazing that there are, because you have all this, whenever you have cylinder, you have these parallel cylinders, and opening up the cylinders will stay in your affine invariant manifold. So, okay. maybe I should. And some of the, just actually based on Smiley-Weiss result, but I am not going to talk about that. So maybe I should mention the theorem that, and I put it in quotation, unfortunately. So I make the theorem vague, but I'll give you a corollary at least, because unfortunately I won't be able to define things properly at the end of my talk. So if M, so this is affine SL2 invariant. Okay. Okay. So I thought a little bit about how to present this, but I hope this makes sense. And I'll give you an example. Boundary of M. Boundary of M means that we have a sequence of points in M going to the boundary of H A1 to AK. Is, okay, so if you do it so generally, you get something which is, you can take the orbit closure of the points that you get, and it's SL2R invariant. For example, you can have, if maybe you start from this surface, you have two parallel saddle connections. Take a sequence of these points in M, and you can construct them using just geodesic and horocyclophore that will make only these two guys very small. Use GT, then use HT, non-divergence, go to infinity. Okay, and then take the SL2 orbit of that. So my dream is that if you understand the boundary, you should be able to understand inside, right? I mean, and do it inductively, because when you go to the boundary, something goes down. But okay, so it turns out to be more complicated than that if you want to apply this result. But at least it's true that this is inside boundary of H of, I apologize for the statement, of expected dimension. So what do I mean by that? So if I get rid of these two guys, there's no additional surprises. Just you get into what you can sort of see. So if I squeeze this and this cannot, for example, if you squeeze these two, and if you get everything on the boundary, the place you're lying, then you started with everything. So the dimension goes down as it should, and you can't just get another, it can't be bigger than what it should be. Maybe I will give one statement which is behind this, and at least it makes more sense because the boundary, I'm not defining it. So maybe the proposition which is behind this, at least behind half of it, is that if you look at points in, if you have M, which is affine, and write down R of M, the set of ratios in M, is the set of all R's, which is R is the ratio of two parallel cylinders on some Q in M. Is that
the moduli or the
generic? So the ratio of, the lengths or moduli, your choice, yes, both. Or two, like if you have, for example, some places you have these two parallel saddle connections, generically parallel to each other locally, and the ratio is maybe, they all belong to that field F, is 10, and sometimes it's 200, and sometimes it's square root of 5, or sometimes 2 square root of 5 plus something. If you write down all these numbers, this is a finite set. So it's bounded, depending on M, of course. generic means that you take the ratio of two cylinders, which are, say, two cylinders which are parallel generically locally, meaning that inside U, all the points of M intersection with U, these two cylinders are parallel. So there are some, like one cylinder being square root 5 times the other cylinder is a linear equation in Q square root 5. So you just look at the things that are coming from parallel guys, and this would be a finite set. And so maybe I will, I want to say a few words about the proof of such a statement, but maybe I'll mention another theorem because I want to write the theorem without quotation. And I have high hopes for this theorem that will give more understanding of these affine invariant manifolds. But the theorem, for example, would say the nice thing about it is that you can always go to the boundary the way you want and get something easier. For example, it sort of suggests strongly up to, if you forget about how you might disconnect the surface, that if you have higher rank things, there are algebraically, there are some Veitch surfaces behind it, meaning that if you have some field F, this is defined in field F, then you have like Veitch surfaces which are defined over the same thing, and there's so many, even stronger than having a Veitch surface. And you can try to start from something that has a rank and try to make the rank smaller and smaller, go to the boundary, make the rank smaller, and do it inductively. And so here is a sample theorem that one can prove using this, is that if rank of M is G, which is the maximum possible, then M is sort of either M is H, one of the components of this, or hyperelliptic locus. But that's kind of the type of argument, at least this is the first thing that we can do sort of precisely using the inductive argument. But it's probably, so that my remark would be that this probably, I expect the proof to work, so it should be maybe even if rank is bigger than G over 2 plus 1. So before you hit the first possible ramified cover from lower dimensional, this kind of argument is, if you don't have anything, then you can prove that inductively you don't have anything. Once you have to prove that you actually some stuff that exists, it's much more tricky because you have the lower dimensional thing, but you want to see, can you patch them together to build the thing inside? And that seems to be more tricky that I was dreaming. so maybe, but you can rule out high rank things. And so, for example, this would mean that if you have some V little patch inside H1, A1 to AK, and if you have, so I draw V as like this, it's inside some U, one of these charts, and it's defined by only equations on relative homology. If you just put any condition that you want on relative homology, but a restricted type of conditions on absolute homology, the result with Eskin Mohammadi, and using this theorem would imply that the SL2R times V is basically the orbit closure of this is the whole H, or hyperelliptic locus. And if you can rule this out, or even in this case, what you get is that, for example, if you have such a V, if you have put these conditions, you can find cylinders which take the right rate, whatever ratio of the volume that you want, or for a generic point, and you can basically see what the SL2R orbit is, because if this happens, it's basically you get into the full rank, and probably up to rank half G that it's safe to do that. Do I have a few more minutes, or?
6 minutes over time.
Okay, so I apologize. That I wanted to say a little bit about the proof, but maybe I just say a sentence that is, even though it's about SL2R, what I think is the most important thing in some of these things is actually using the, and even I think Alex Wright's result uses Smiley-Weiss, using the minimal set for the Horst cycle flow, and also for the proof of this, even the proof is not complicated, but it uses non-divergence of the Horst cycle flow. So even if you want to just do the SL2, any statement about the Horst cycle flow will have consequences which are completely non-trivial for the SL2. So I think the main thing behind this is non-divergence of the Horst cycle flow, and I hope that next time I give a talk at MSRI, we know more about the Horst cycle flow. But thank you.
Can you explain this point in more detail again? I don't understand. What is V?
So it's actually, so V is some subset inside some open set U. It's not a.
Is it a linear? Just subset. Okay.
No, it's defined by some equations on the REL only. It doesn't even have to be. So what I want to say is that when is SL2 orbit, everything, SL2 orbit is some affine invariant manifold. If you can't fit V in some affine invariant manifold, then SL2 orbit would be everything, right? And if you don't have anything on absolute homology, you are forced to have something which is full rank, which will be everything. Now, there are examples of this, but actually, so I hope this is okay. But there are examples, like it's a families of billiards. Okay. Okay, it's like a families of, I'll give the simplest example. This is Alex. Okay, this should be checked. But I believe that's one example. Like this, these are, the angles are pi over 3. It's just some genus 3. If you unfold this, you get some genus 3, right? And if you just allow these things to move parallel but arbitrary, this is Alex, right, has this so arbitrary, moving it around, then actually then you unfold it, so there are examples like this, like families, natural families of billiards. Then you want to say the generic element in this family is really has cylinders which take up like between like two numbers, or at least 99.9% of the volume, or things like this. And for that, like you can see that if you unfold this, I think you can check that there is no, you can't fit it in. You have equations on, you might have things on REL, but in absolute homology, you can't fit it inside things which are linear equations, absolute homology. So then you basically, so that's the type of applications we have in mind, that you have these families, but then maybe there are even equations relating like REL and absolute homology, but they are in a way that you can't fit them inside anything except for full rank. And if you know full rank is everything, then you can, and you can rule out that it's not hyperelliptic case, then you get this statements like this. But of course, you would like to know all the invariants of manifolds and be able to do this in general, but it's just one.